Hi, welcome to our first problems and solution sessions of geometrical optics. So today we are going to look at several problems in geometrical optics and we are going to explain how to solve those problems. But first we need to revise some fundamentals as well as bring in some concept from the modern physics. So this session we are going to solve problems in geometrical optics. So the first concept we want to borrow from modern physics is about relationship between velocity of a light, frequency and the wavelength. As we were discussing Huygens principle, we realized that light is an electromagnetic wave. So its velocity is equal to wavelength into frequency. We also know that different frequency of light has different colors and the velocity is equal to wavelength into frequency. So we can simply write V is equal to wavelength, usually denoted by lambda, multiplied by frequency. We are going to call it F. You can read about all that in a wave optics course, but this is just a starting point. Here the lambda has to be, lambda should be in meters, and frequency F has to be in hertz, whereas 1 hertz is equal to 1 second to the power minus 1. So when we do that, basically the unit of velocity is going to be meter per seconds. Okay. Now let's define nanometer, where 1 nanometer or nm is equal to 10 to the power minus 9, as well as Armstrong, which is shown as 10 to the power minus 10. Hence 1 nanometer is equal, sorry, 1 Armstrong is equal to 0.1 nanometer. Now we may have observed in many experiments that when light ray travels from one medium to another, color does not change, which means that the frequency of the light when traveling from one medium to another, let's say from medium 1 to medium 2, the color of light remains same. So we can conceptualize the concept here. The frequency of light remains same when the light travels from one medium to another. Of course, the velocity changes, so as the wavelength, so that this equation which we written here, velocity is equal to wavelength into frequency. So the wavelength will decrease as the velocity also decreases from one medium to another. Now we are going to revise one more concept where we said here when we introduce refractive index, we said that it is nothing but velocity of light in vacuum, that is c, divided by velocity of light in that particular medium. So c is usually three into 10 to the power 8 meter per second, that we know, and velocity of light, and we know that the velocity of light in vacuum is the maximum, so n has to be always greater than or equal to 1. Okay, so with this background, we'll start solving few problems and see how we can learn from them. So here is our first question. It says that determine the change in wavelength of the red rays during the passage from vacuum to glass. If the refractive index of the glass is 1.5 and the frequency of red rays is 4 into 10 to the power 14 second inverse. So frequency f is given, which is 4 into 10 to the power 14 second inverse. We can also say that same as 4 to the power hertz. Okay, now the refractive index of the glass is given, which is 1.5, and we have to find the wavelength of the light, right? So wavelength is unknown. So here, thinking about that, let's try to visualize the problem, right? So the ray of light is actually traveling from vacuum to glass. And now at this point, when it enters the glass, some things will happen, right? We know that frequency will not change, right? Velocity will change, and lambda or wavelength will change. Now, assuming that the frequency is constant, right? So we have to find a relationship between velocity and lambda and frequency, and we are going to use that equation to basically derive the value of lambda. So we know that the velocity of light in glass here is going to be equal to wavelength in glass multiplied by the frequency. Okay, and we have to find this wavelength first and then compare it the wavelength in vacuum, right? So we are going to say wavelength in vacuum was V. Okay, now wavelength in vacuum, we know it's delta V, and wavelength in the glass is delta G, and we know that this one is greater than this one, so the change of wavelength is going to be delta V minus delta G, and this is what we have to find. Okay, so first let's try and find out this one, and then second we try and find out this one, which will be delta G Vg by F. Okay, and once we are able to find these two, delta V and delta G, will be able to arrive at the result. Okay, so now we need a relationship here, Vg with the velocity in the first medium, right? So let's write few equations. So in the medium one, which is vacuum, the velocity of light will be c. Okay, this will be equal to lambda v into f. Correct? Now, when the ray of light enters the medium glass, it will have a velocity, it will be lambda glass, but the frequency will remain same. And now we know that n is equal to c by v, so v will be equal to c by n. So we are here going to write c by n is equal to lambda g into f, and we know c, that is constant, 3 into 10 to the power 8, n is given here, f is constant, so we can easily find delta g will be equal to C by NF. Okay. In here, we are going to find lambda B will be C by F. And now simply, as we said, we need to determine this difference. So we are going to write here delta V, lambda V C by F minus lambda glass C by NF. We can take out C by F outside. We have 1 minus 1 by N, and that will give us the answer. We know C, we know F. C is equal to 3 into 10 to the power 8, and we know N. When you plug in these numbers here, we'll get the answer, which will come to 250 nanometer. Hence the problem is solved. It's just thinking through the problem. Basically, we determine, we have to first understand how the light is going to behave from one medium to another, and then we have to find those relationship between these equations, and we'll be able to arrive at the answer. Now here is the problem number 2. It was found that the refractive index of one type of glass is equal to 1.5 for the red rays and equal to 1.54 for the violet rays. Determine the velocity of propagation of these rays in the glass. So here we know the refractive index N for the red ray is 1.5, for the violet ray is 1.54, and we have to determine the velocity of propagation of these rays. Now simply by using the definition of refractive index, NR will be C divided by velocity of red ray. Okay, so velocity of red ray is going to be C divided by NR, and we know C and we know NR, and we can easily find velocity of red ray, and when you do that, plug the numbers, it is going to be 2 into 10 to the power 10 centimeter per second. Okay, similarly we can do this for NB is equal to C by VB. This is violet, so velocity of violet ray is going to be C by NB. We know the NB is here 1.4, this is 3 into 10 to the power 8 meter per second, and we will arrive at the answer 1.95 into 10 to the power 10 centimeter per second. Okay, so very simply using the same equation by the definition of refractive index, we can solve this problem. So let's go to the problem number 3. So this is our problem number 3. A light wave of frequency 5 into 10 to the power 14 Hz enter the medium of refractive index 1.5. In that medium, the velocity of light wave is what and the wavelength is what, right? So we know frequency here, frequency is given 5 into 10 to the power 14 Hz. This is the unit we want. Medium of refractive index 1.5, so N is equal to 1.5. Now the velocity of light we can simply find out by using the definition of refractive index, which is N is equal to C by V, right? So we can find the velocity will be equal to C by N. C we know 8, N is 1.5, we divide it by 2, we get 2 into 10 to the power 8 meter per second. So we already solved the first one. Now we know the velocity and we have to find the wavelength. So we are going to use a simple relationship. Velocity is going to be lambda into frequency. and we know we have to find this one. So lambda is equal to b by f, right? So when we do that, v is the v is 2 into 10 to the power 8 per second, and the frequency is 5 into 10 to the power 14 hertz. And we can simply find the exact number. So this was a question taken from IIT JEE. So you can see, if you know your fundamentals, you can simply solve this problem very easily. Now coming to the next question, which says that wavelength of light is 6,000 Angstrom, and we know the unit of Angstrom, right? So lambda is 6,000 Angstrom, or 6,000 10 to the power minus 10 meters, okay, in the air. Now it is going to enter a medium with a refractive index 1.5, right? So lambda is going to decrease, so as the velocity is going to decrease and frequency is going to be same. Inside the medium, frequency is what? That's what we have to find. So let's simply find out the frequency of the light in the air itself, right? So we can find that by C is equal to lambda to F. So the F will be C by lambda. The C is 3 into 10 to the power 8. And the lambda given here is 6,000 to the power minus 10. And we can simply solve that and we'll get the answer for the frequency, right? So inside both the mediums, the frequency is going to be the same and its wavelength is going to change, right? So we now need to find out the wavelength, okay? So very simply, let's solve for the frequency. The medium one, the velocity we know is, the frequency we know, and we know lambda already we know here, which is 6,000 Angstrom, and we have to find lambda in the other medium, right? So in the other medium, we write the equation like this. So the velocity in the another medium is going to be equal to lambda I into the frequency, okay? Now we know the frequency is not going to change, so we can simplify lambda I is equal to b by f, and we already have a frequency here, which is going to be equal to b by f is equal to c by lambda, and then we go to the top. And now, so we have this lambda I. Now V is going to be, we can derive that from the refractive index, right? So refractive index C by V. So the V is going to be C by N. So we are going to put that here. So instead of V, we write C by L into lambda divided by C. And as you can see, the C will cut. And basically, this is going to be like that. So very simply put, we know the initial 6,000 Angstrom divided by 1.5, and you know the answer. So simply by plugging the right numbers in the right equation, we can find the answers. This is a very simple problem. This is also from IIT JEE. The next question: when a ray of light enters a glass slab from air, its wavelength decreases, its wavelength increases, its frequency decreases. Neither of that happens, right? As we know, fundamentally, the ray of light is going to enter from air to the glass, okay? So frequency is going to be the same, that we know, because the color does not change. Now velocity here is higher, which is c, and here it is less, so velocity is going to decrease, and we know that velocity is equal to frequency into wavelength. So in order for that to happen, the wavelength also has to decrease. So the answer is wavelength decreases, this is wrong, frequency decreasing, wrong, this is wrong, so the answer is D. Now, going to the next question, which says that absolute refractive indices of diamond and glass are so and so forth. What is the ratio of thicknesses of this material if the time of propagation of light in them is same? Okay. Now this involves light kinematics. So we are going to say this is our diamond. And this is our glass. Okay. This has a refractive index 1.5. This is a higher refractive index 2.42. Means light will travel slower here. Slowly here and faster here. Okay. Now it says that it's going to, when a ray of light enter from here and here, basically the time of propagation of them is same. This means in a time t, it is going to cover a distance d glass, and here dd, which is a distance in diamond, right? Now it is going to be slower here, right? So it will in the same time will travel a less distance actually, right? So this is going to be the d, and here more distance, right? Because here it is going to run faster for the same amount of time. So here it will travel this much, here it will travel this much. So we drawn that with a guess, but now we know how it looks like, right? So we have to find the ratio of this material. So we have to find the ratio of these two, that how much the distance is, right? So we have to find the ratio, which is how much distance will travel in the glass divided by how much will travel in the diamond. Okay. So to do that, basically we have a time and we know how much distance generally it will travel will be the velocity into time. Okay. So we need to know the velocities. The velocity of light in diamond is going to be very simple. So we have this refractive index of diamond is going to be c by velocity in diamond. So velocity of diamond is going to be c by nd. Okay, and velocity of so similarly for the glass we can write, so velocity in the glass is going to be c by ng. We both know all this, right? The distance, the time is same, so the distance, let's say, let's reread the question and we have to find the right ratios. So absolute refractive index, diamond and glass is so and so forth. What is the ratio of thicknesses of this material? So we are going to find the ratio of diamond versus glass. Okay. So let's find so we know the velocity now. So we are going to multiply that with time. So this is Vg, same time for the glass, divided by velocity of diamond, same time t, and this is the ratio we want to find. T will cancel out, so it will basically Vg by Vd, and Vg is here c by ng, which is the refractive index, divided by c by nd, which will be equal to md divided by ng, and hence we have our answer. Nd is 0.42 divided by 0.5, which is going to be 1.61. Okay, so sometimes the question will ask for the ratios, and if we know the fundamentals, we'll be able to calculate that very simply. Now, moving on, basically here we have a plane mirror AB which can rotate about a horizontal axis O. So just look at the picture first. So here we have a plane mirror AB which can reflect the light. So if the light is coming like this, it reflect like that, and it can rotate about this axis O, and it says that the light rays incident on the mirror at an angle alpha. Okay, by what angle will the reflected ray be rotated upon the rotation of mirror through an angle beta? It is saying that, so here the light ray is coming, it is getting reflected at angle alpha, hence the angle of reflection is same. Now if we rotate the mirror by an angle beta, this will be also same. How much the light ray will turn? Okay, so let's try and solve that. So here is our mirror. Here is the reflection happening. Sorry. So here is the reflection happening. We know this is alpha. And now if we turn the mirror by an angle beta, what will happen to the light ray, right? So light ray is going to be again incident like this only. Okay, but now the normal will shift, right? So it is, here is the new surface. Okay, we are going to redraw our normal. So whenever we are doing a problem of refraction or reflection, we always redraw our normal. So normal will change. Okay, and basically the normal will rotate by an angle beta, right? Because we rotated the, so this was the initial normal, and now we rotated the mirror, so this normal will rotate by another angle beta. Okay, so now the angle of incidence for this mirror is going to be this alpha plus beta. So the new angle of incidence right? So this was our previous normal. Now this is our new normal, and now this is the light ray which is coming like this. So now the angle of incidence is alpha plus this beta. Okay, hence it will reflect like that at an angle alpha plus beta. Okay, so the new angle at which it will go will be basically the whole deviation from here all the way here is going to be 2 alpha plus beta. So earlier it was 2 alpha, now it's going to be 2 alpha plus beta. So we need to find by what angle with the reflected will be rotated. So initially it was just going 2 alpha, and now it will rotate it by double of that basically. So we're going to say so it will rotate by 2 beta. So if you rotate the mirror by an angle beta, basically the reflected rays will rotate by double of that 2 beta. So that's our answer. Now this is our last problem here for this session. So in here a light ray is propagating along a horizontal, is incident on a vertical screen. Okay, so let's try and understand that first. So we have a light ray which is source. It's coming like this straight on a horizontal screen. So this is our screen. Okay, it's coming vertically. If the plane mirror is placed on the path of the ray like this, the light spot on the screen is displaced upwards by 3.5 centimeter. So when we place the plane mirror, it will reflect the light like this, and basically saying the H is 3.5 centimeters or 3.5 meters. So never mind. So it's 3.5 centimeters. Determine the angle of incidence of the ray on the mirror if the distance between the mirror and the screen is 50 centimeters. So Mirror and the screen, the distance is 50 centimeters, so we also know that. Now this is 50 centimeters. So these are the two things which is only given, and we have to find the angle of incidence I in this case. Okay, so think about that, right? So they have given this distance and this distance, and we will be able to find this angle alpha here, right? And somehow if we can find, we will be able to find alpha, okay, by taking the ratio here. And if we are somehow able to find a relationship between alpha and I, then we can find the I and the problem will be solved, right? So they are asking us to find I. So let's put some effort to first actually find a relationship between I and alpha, and this is how we are going to solve the problem. Okay, so this is our strategy. So first, let's write down about, so tan of alpha is going to be 3.5 divided by 50, and as you know, it is a very small compared with 50, so this is also equal to alpha, assumed equal to alpha by assumption. So which is, so alpha is going to be h by L here, okay, and the alpha is h by L, so we have already found alpha. Now we have to find a relationship between I and alpha. So let's look here, let's find out that. This is our straight line, okay, and there is a mirror at certain angles. We are going to put the mirror now. We do not know at what angle this mirror is, right? So we are going to say this is certain angle, and this is, say, it is theta. This is also going to be theta by definition. So that's the angle of the mirror. Now before we proceed, we basically draw our normal first so that we can deal with the reflection. So here we go. Perpendicular to it, to that point. This is our normal. Very well. And now we know the light ray is coming like this. So let's draw that light ray. It's coming like this. And this is going to be our angle of incidence by definition. So this angle is going to be I, and we know that it is going to be reflected back at the same angle. So we are just doing it step by step, and it's going to be reflected back at the same angle here, and by definition, by virtue of law of reflection, we know that it's going to be I. Okay. Now they have also given us this angle here, which is alpha. Okay. Now we can see that this is theta, this is theta, this is I, so this is going to be also I. And theta plus I looks like 90 degrees, right? Let's write that. I plus theta is equal to 90 degrees. We'll say pi by 2. Okay. Now we have also the difference between this angle. So I, so let's find out this angle, the small angle here, which is still missing. So let's call it anything, and we are going to write, so this is going to be alpha minus theta, right? So this is going to be alpha minus theta, and this I plus alpha minus theta is again going to be pi by 2, correct? So we have these two equations, and let's try and see if we can find something out of it. So we're going to write I plus theta is equal to I plus alpha minus theta. So this one cancels. Basically 2 theta is going to be alpha. We know theta, sorry, so yeah, so theta is going to be alpha by, okay, that's not bad. And now we know we have to find I, so I plus theta, which is alpha by 2, which is equal to pi by 2. So we know I is going to be pi by 2 minus alpha by 2, which is going to be pi minus alpha by 2, and this is I. So now we know this angle I, right, can be found by using this equation. We already have it here. So let's change that a little bit. So we have this here. We know pi is 180 divided by 2, and we know the alpha here, right? So alpha is 3.5 divided by 50, and basically h by L, so we can simply write for small angles I is going to be pi minus h by L, which is alpha. So we already found from here. By 2, we'll have our I. So we simply plug in the numbers. Pi is 3.14 minus h by L will be 3.5 into 10 to the power minus 2, because it is in centimeters, divided by L. So again in meters it's going to be 0.5, 50 centimeter, and here by 2 we'll have our number is 1.53 radian. And this is the answer. So think about it, right? So how we approach the problem, okay, and how we found the solution. So when we looked at it, we can clearly see we know the alpha, right, and we have to find I. So somehow if we can find a relationship between I and alpha, the problem will be solved. So that was our approach. And because this one is smaller compared to 50 centimeter, tan alpha is going to be equal h by L. So we know alpha for sure. And then we endeavor to write some equations to find a relationship between alpha and I, that using some basic trigonometry, we wrote 2 equations, solved them, and basically found that relationship here, and then plug the number to find the answer. So this was the first problem set we did, which will be followed by few QEs. And in the next session, we are going to solve problems of law of refraction and Snell's law, law of refraction, which is very important. And then we'll move on to basically the critical angle and total internal reflection, and that will be the set before we move on to the tracing the rays, basically the lenses and optical system and their combinations.